So we are recording now. Um, and we're going to switch over to the whiteboard actually. Whiteboard. So, yeah. Okay. All right. So the topic that we're discussing today is, as I said, SVD, which stands for singular value decomposition. Decomposition. Okay. So this relates once again to having data, right? So let's start with our classic example of the iris data set. So I have iris, and we use iris a lot because it's something that we remember, right? So we've got 150 samples, and if I have one column of values for every sample, S1, S2, all the way to 150, call it F1, that is equivalent to having one axis in a vector space. Do you see that? F1. That's one axis. A vector space, we can corroborate that by looking at this three-dimensional space. Every axis needs to be 90 degrees from the other axis. Do you guys agree? So we have, for instance, right, the next one is this one, that's 90 degrees. That term, mathematically, because we can't really visualize it in higher dimensional space, is called orthogonal, right? So that's it. But just intuitively think of it that way. One axis, second axis. Where does the third axis go? Up, right? And it's got 90 degrees on this one and 90 degrees on this one. So you can see it's like that. That's a vector space. So as we add another feature, F2, what do we have? Another axis. Why? Because a sample in these spaces is a point, right? That's what it is. So if I have a 2 and I have a 7, so that means 1, 2, and then on F2, 7. 1, 2, 3, 4, 5, 6, 7. Do you guys see that? 2 and 7. So it's a point. A sample is always a point in a vector space, okay? Regardless of how many dimensions. So now I add F3, another column, and then, I'll add another one later. So that's another axis, right? Another axis. Do you see that? And that's F3. But what do we know about the iris data set? The iris data set actually has 4 features, right? What are they? Petal length, petal width, sepal length, sepal width, right? You should know this because it's your reference. So we have to add another column of values for each sample, call it F4. Now, the problem we have now is we have no way of visualizing 4 dimensions, right? But it obviously exists, and the math holds exactly the same way. So I'm gonna just have to draw it this way, but we're gonna call it F4, but we have to agree this one is also what? 90 degrees from the other 3. Do you see that somehow? Mathematically, it will hold, even though there's no way, unfortunately, that humans can visualize anything in higher dimensions. And I could just keep adding columns here. I could have 1,000 columns, and then how many axes would I have here? 1,000. Do you guys see that? Right, so this is a very fundamental concept that you must understand. And everything is always a point. The sample, one row, S2, is going to be a point somewhere in that space. And therefore, we have these properties that we want to understand. Okay? So, also, we know that this is now data that is two-dimensional, right? So it's going to be M, and I should say M by N. What is M? 150. What is N? 4. It is M by N. That's our data. Okay? So we have this shape. And so it becomes a matrix. This is a matrix. Oops. So one fundamental concept that from now on we have to understand is that it's not efficient to process every single one of these values individually. That's key to understand. It's just not efficient. If AI, right, like ChatGPT that you guys are familiar with, or something like that, Claude, if you had to process all the values in these matrices one by one, we wouldn't have ChatGPT. It's just too slow. It takes 3 months to train ChatGPT with all the text in the world, and in in a level in over a cluster of GPUs. So not only is one GPU in parallel, but you have multiple GPUs in parallel. So that's the only way that it can be done. So it's like me having 1,000 problems, right, that I need to solve. I'm not going to give all 1,000 to you to solve. Instead, I'm going to give you 50, you 50, you 50, all of you get. You all solve them, and then we somehow put together the information. We have to do things in parallel. And so, we're used to multiplying things like A times 7, right? And we all understand this really well. That's algebra. But we need to learn a new multiplication called a matrix multiplication. And you may have seen it already, and I'm sure I've talked about it already, but I'm starting here because it's very fundamental. I'm going to do this lecture twice at least this semester, today in the context of singular value decomposition, and again in the context of neural networks. Okay, so it'll be what one nice thing about this is that it's the same operation always, but we have to think about it differently because it with respects to two different things. So we'll visualize it in two different ways. So the fact that we have the matrix multiplication means that we can't do things individually. Instead, we have to learn the technique to multiply kind of everything in here all at once. Do you guys see that? And then I'll talk to you about like the GPU a little bit. So let me motivate that first, okay? So singular value decomposition. So that means we need an area of math called linear algebra. Now, do you need to know the entire course of linear algebra? No. We actually only need a subset of linear algebra, right, that we should understand a little bit. And this is the operation I'm going to teach you today, or go over with you again. You may have seen this before. But it's essential that you take this thing seriously because it's really fundamental. Now, I will give you a problem set also about these that you will just solve by hand. 20 to 30 little problems should be fun, and it's just of this methodology just so that you practice it, okay? But not today. I'm still working on the problem set. All right, so the question is, what does linear algebra do then for us in AI and machine learning? And that fundamentally, we're dealing with matrices and vectors, right? So we have a matrix that usually has a shape M by N, right? Like iris, 150 by 4. That's a matrix. A two-dimensional array that you guys are very familiar with already. And then we have vectors that are something that is one-dimensional, so usually going to be like probably M, something like that. And we've looked at this before. So then the question is that you want to ask yourself, okay, you're saying that I need to multiply my matrices by values. What about multiplying the matrices by other matrices or by vectors? Do you see that? So, we're going to multiply things kind of in parallel now. That's fundamental. So then you might ask, okay, so if I have a formulation such as A, B, C, D times E, F. What is that? This is a matrix of a matrix time, it's a multiplication, of a matrix times a vector. Do you see that? You just have to understand that. This is important, and we will start to see later on why this is important. And, so then you have to ask your question, and this is there's two things here. I'm going to show you, obviously, the mechanical way that this is done in math, right? Which is not hard at all. You just have to learn a little trick. And then I'm going to give you the intuition of this. Like, what does it mean in this context or that context? So we're going to ask the question, what does a matrix do to a vector? So what does a matrix do to a vector, especially, when you do a matrix multiplication? Okay, there's other operations that you can do, of course. So this is key. So let's take a look at this scenario now in the context of an actual example. So given something like this, so I'm going to have a vector x, and it's going to be 1, 3. Okay, and I'm going to have, so this is a vector, and then I'm going to have a matrix A, and this is going to be 2 minus 1, 1, 1. Matrix. Okay, so then the formulation is going to be something like this. We take A, oh, and my battery. Okay, so we have A matrix multiplied with X. So we're going to do a matrix multiplication of A, the matrix, times X, the vector, and that produces Y, which is another vector of the same dimensions as X. Okay? So the question is, what does this actually do? Like, what's going on here? What's the outcome? All right, so let's do first the operation. Very simple. Okay? And then we're going to talk about GPUs. Okay? This should be important to you guys. Anyone know how much NVIDIA is worth right now? Anyone know this? Trillions of dollars. One of the most valuable companies in the world. I don't remember off the top. I think 2 trillion. So it's worth a lot of money. Right? And what does NVIDIA do? It makes NVIDIA GPUs. And what do NVIDIA GPUs do really? They do a matrix multiplication very efficiently. Do you see that? This is really important. Okay? So let's do the operation first, and I'm going to do the simplest thing that I can think of. Okay? So I have my data. All right, so how does it work then? So I have the matrix 2 minus 1, 1, 1, right? And then 1, 3. And this is going to give me something like this. So how does this work when you do this operation? So you do this. I have this like mental trick that I always do when I need to do a matrix multiplication. I do this. Like that. You see this with my hand? So that means that the dimension of the row here needs to match the dimension of the column here when I do and then I multiply row times the column. So here I'm saying, and I'm going to change the color here to yellow. So I'm doing 2, 1 times 1, 3. That's the first operation that I do to produce the value that goes here. So how do I do that? I do 2, and here I can probably darker color. So I use 2, 1, 1, 3. And the result is added together. Do you see that? And if I have 4 values here, then I need to have 4 values here, and it's the same thing. Each one gets multiplied, and then they get added. So you can see 2 times 1, 1 times 3. You can see why I'm doing that. It's like I'm putting my fingers here. Like if I do this, 2, 1, minus 1, 3. Was it 3? Oh, minus 1, 1. Like that. And then 1, 3. So I do this to produce that, to produce the other one. And that's a very helpful mechanism. And as I said, I'm going to create a problem set for you guys to work through and do this as a homework a little later. So, we're going to be, because this is so fundamental, right? In neural networks, I will do this again, right? All right, so we do this 2, 1, 1, 3. What is that equal to? That's going to be 2 plus 3. So that is what? 5. There you go. That's my 5. All right, then I do the next one. So I'm going to do minus 1, 1, 1, 3. Right? So I just repeat the process so that we can write it out over here possibly. I'm going to say minus 1, 1, 1, 3. And I add them. Okay? So that should give me minus 1 plus 3, which is 2. So the value here is 2. So I do, and that produces 5. So this and that gives me 5. This one and that one gives me 2. Just like that. And we do this, and if I have more, I could have 3 here, then I need to have 3 here. That's what the fingering tells you, that the dimensions must be correct. If you don't get those, you get an error, or you can't do the calculation. Okay? So this is a really important operation that just exists, and it's just a thing, right? But it's really important because we cannot train anything by individually looking at the values. So we have to, in parallel, if you will, do these operations, and that's where, if algebra is the CPU, then linear algebra is the GPU, right? Or if algebra is like the sequential approach, then linear algebra is the parallel approach. Do you see that? So that's essentially the idea. Okay, so I did the operation here, and I get that one. So that's just the mechanics, okay? Everyone with me? Now, what's interesting about this is I can give you, as I just said, this operation is essentially, it's very important for machine learning, but to do things in parallel, or to do things, and another way of saying this is just to do things faster. So you'd be surprised. So, maybe you guys knew or didn't know that one of the biggest companies that makes these GPUs is called NVIDIA. Maybe you've heard of it. All computers have a graphics processing unit, right? That's a thing. And those were created for the graphics to be faster, right? So you'd be surprised to know that actually NVIDIA created these GPUs not for AI, but for, can anyone guess? And for what specifically? Video games. Video games. So that was their industry. That was their target. Yeah, they wanted obviously great graphics, but it was all the gamers. So when did we get this? The biggest development happened around 2007. That's when it was like a game changer. All right, in 2007, they produced a product, the GPU, and I'll give you the analogy, which is similar. In a computer graphics game, right? So a video game is a vector space. You agree, right? If we exist in a vector space, a mesh, first-person shooter, a car, whatever it is also, right, in a graphical environment with 3 dimensions. You agree with that, right? So let's imagine it's the same idea. Let's switch over to red. So I'm going to use a 3-dimensional space, which in this case it is definitely 3-dimensional. And I have a first-person shooter. So what is a first-person shooter, or whatever video game you like to play, right? What is it? It's something called a mesh made up of points or little triangles, right? That's essentially what graphics are. So you have a point, a point, a point. They form a little triangle. Then you have another point, and guess what? And then with that, you start creating the mesh that looks like whatever it is that you're, rendering, right? So then I'm gonna skip the triangles and just stick with the points. But you can see here, all these points, as I start drawing them literally on the screen, guess what? It looks like a person, correct? Do you all agree? So if I'm building a video game, what do I need to do to this person if it's interactive? They need to move, correct? All right. How do I move all these points? Well, I could move them one by one sequentially through the CPU. But what's the problem with that? Let's say that my goal is to move them here. So how is it going to render if it's sequential? It's going to render like this. It might be fast, but still, if you remember, some games used to have this lag that was really annoying, right? Of rendering like that. That's not fun, right? To play with a game that start to see the head and the feet still haven't appeared, right? Especially if you're rendering lots of things and as it gets more complicated. So how did they solve this? Well, they created the GPU. So this is with the CPU. It renders kind of sequentially, let's say up, from top to bottom, something like that. The GPU, what does it do? It takes all the points all at once and it just moves them, right? It creates I'll do this effect, but it's like all points are appearing all at once. So there is no lag, it is much faster. And how do we achieve that? By doing a matrix multiplication. So you can think of this vector per se as one point. So then we can create a whole bunch of these points, right, and perform the matrix multiplication with some matrix A, and now all the points get moved at once because the GPU has multiple cores and everything, and it's essentially doing this operation called the matrix multiplication. CPUs do other things. Like CPUs are really great for what they were designed. They're great for, obviously they're the central processing unit of any computer, but they're not great for this specific task of rendering a mesh from here to there quickly. We want it to move quickly, right? You want to have thousands of soldiers and thousands of buildings and things like that. Rendering all of that, takes a lot of power. So GPUs were created. And what they do is essentially they perform this operation called a matrix multiplication. So an entire industry worth $1 to $2 trillion focused just on in hardware doing this operation efficiently. Do you guys see that? So as it turns out, machine learning, so I've given you the example of you have a mesh, that's the data, some matrix, you multiply times another matrix, that these are called rotation and stretching matrices, and you're able to move your mesh however you want to. All right, so there's a whole industry dedicated to this operation. As it turns out, though, we can use this matrix multiplication operation for lots of things, not just computer graphics. We can use them whenever we need to multiply a lot of things together, as long as we follow. Do you guys see that? We just have to learn mechanically that operation. All right, so hopefully that makes sense as far as that. Now we're going to get into, so I've given you kind of like why this is really important, right? Started for games. So in 2007, it happened really quickly too, I should say. So it happened in 2007 that the GPUs came out for video games, and by 2012, they were already being used for machine learning and AI. They really quickly picked it up. Right? And so, so that's the idea. So now let's focus a little bit more on the matrix multiplication and what it's doing to this vector, right? So that's the question we're going to pose again. So what does a matrix do to a vector? Now, the operation, matrix operation, is the same one that we're going to use throughout the semester. Always the same operation. But we're going to look at it it's going to have like a different focus, sometimes, right? So we're going to look at it from the point of view of vector spaces today. All right, so our focus today is to understand it from the point of view of vector spaces. So I mean a space where points live, right? That we have discussed. Later on, we're going to learn how it is used to represent neural networks. You might be surprised that a neural network is just a whole bunch of matrix multiplication. Okay? So we'll see that, but it's the same operation. So now let's think about this. So what does a matrix do to a vector? Well, we had initially so now our vector, that we're talking about is the original one, 1, 3. So that was the vector x. And the question is, this is a vector. What does it mean to be a vector? Second, we have this matrix, 2, -1, 1, 1. If we multiply this matrix times this vector, the question is, what is this matrix A doing to vector x? Do you guys see that? That's the fundamental question that we want to understand. And so we know that it produces, or you can say that in this case, it transforms x into y. So we're essentially taking x and we're transforming it to y. And we know that if we perform the operation, the result was 5, 2. But what does it mean graphically? So what happens? All right, so now we can take a look. So there are a couple of ways, there's a couple of ways that you can represent there's a couple of ways that you can represent a vector, okay? In this example, I'm going to use the more classical representation of a vector, which is something like this. So the original vector is 1, 3. All right, so we're going to say that this is this one axis. So it's going to be, let's say, K1, K2. All right, so we're going to do, oops, K1, K2, okay, like that. So we have numbers 1, 2, 3, 4, 5, 6, 7. Numbers 1, 2, 3, 4, 5, 6, 7. So x is 1, 3. So that means it is 1, ... 1, 2, 3. Okay? So there. It comes to there. But sometimes you represent these things as just a point in the space, or sometimes you want to represent them as things that have a direction from the origin. So and actually let me redraw that in another color. So it's going to be that this is our x. Do you guys see that? Okay. Now if you look in this example, this blue arrow, right, looks a lot like an axis. Do you see how they're very similar? This is important, this connection here. Because here we're talking about a vector space of size 3, right? A three-dimensional space made up of all these axes, right? And if you just take one axis, it looks exactly like this one. They are in fact the same, so they are vectors. Do you see? So this is important. All right, what happens to x when we multiply it times a? It was transformed. Do you see that? Into 5, 2. So what does that mean? It means that now we have 2, 3, 4, 5, right? 5. And we have 2. So 1, 2. So that's going to be sort of like that. So if you notice, we transform the vector x into the vector y. Do you see that? This is actually really important. So what did we do actually? Well, let's think about it, right? One thing that happened is we rotated x. X was like this, and we did this. Do you see that? We rotated the vector. This is really important. And another thing, if you look at y, it's a little bit longer. so we also stretched it. So essentially, what does a matrix do to a vector? In the context of a vector space, it rotates it and it stretches it. You see that? So it rotates and stretches the vector. Does that make sense? This is really important, actually. Do you have a question? Yeah, it could shrink it. Yeah. Transform is a great word. Yeah, yeah. Yeah, very good. And this is important in terms of vector spaces, right? So you remember we had talked about compressing things and things like that. So transform is a great word, okay? So what happened? What happened is the question. And the answer is we transformed one vector x, the little arrow just means vector, into another. So now that you know this, okay, let's assume, okay, if I can change one vector, I can stretch it and rotate it. What about all the axes in a vector space? Could I possibly stretch them and rotate them? Do you see that? And the answer is yes. And this is really important. So, I wish I had brought like my Rubik's Cube, right? But actually I can use, you have a Rubik's Cube. Really? Okay. Yeah. Oh yeah. Great. Right? So think of this as a three-dimensional space. This is a Rubik's Cube, right? And actually it's got the right color. So you have the data represented as points in there. But what techniques like, doing these operations can do is they can rotate the space. They can also stretch the axes, which essentially is like if I made this Rubik's Cube bigger, imagine it becomes a bigger cube. Do you see that? But rotate it again. And when you do this, you can change the positions of the points inside. And that's really the key idea, right? If I make from this, I go into this big, imagine, this is a good example. I take the Rubik's Cube and I stretch it to be this whole room. Do you see that? Now the points are kind of like more spread out. Also, I can stretch just one axis more than the others. Do you see that? Like I could stretch this whole thing out as big as this room, but on this axis, I keep it this big. So you can see that the points inside somehow get pulled with that space as well. Do you see that? And so machine learning is really good at that. That's like the underlying fundamental trick of machine learning. That it says, okay, I can't really say what's going on with these points. It doesn't make any sense to me right now. I'm going to try other things. So it just stretches it, and now the points move, and it looks at it again. And it's like, oh, okay, now I see a better pattern. Do you guys see that? And the thing is, machine learning has what? Training data. So it always has the input and the output. So it can, imagine it can just randomly, it takes this cube and it stretches it. And now it moves the points, right? And now it runs an input, gets an output, and it can measure performance. And it says, okay, that was not a good technique. What do I do then? I'm going to stretch it like that, going up and down, but keep it this narrow. The points move in that space, and it tries again. Inputs, outputs, measures the performance, and it's like, that was a little bit better. Okay, so I'm onto something. So maybe I am going to stretch it up that way and this way, and this I'm not going to keep as narrow. I'm going to stretch it just a little bit more and a little bit more, and maybe that improves the results again a little bit more. Do you see? Because you're moving the points inside. Do you guys understand that concept? Any questions about it? So there is that, right? So the machine learning, the AI is doing that. But it needs to do that through an operation. And what's the operation that allows you to rotate and stretch these axes? The matrix multiplication. Do you see that? So that's the whole trick. Any questions? All right, so let's keep looking at it. Thank you for that. You know, and this is only assuming, of course, that we're keeping things in 3 dimensions. But there's also the possibility that I can compress it to fewer dimensions, or I can add more dimensions, right? And so these are things that we're going to talk about later. But for now, let's just stay with this idea. We want to make that Rubik's Cube, rotate it, bigger, make one axis longer than the others, and we can try multiple variants of that. How do we achieve it? By having some vector 1, 3, which is, let's say that's my vector 1, 3, for instance. This is called a basis. In the context of vector spaces, you have 3 axes here, and that's the basis that represents the space where you put points in. Okay? So if this is, let's say this one is dot x, then I can find some matrix, right? Right? A, and then I do a matrix multiplication, and I transform x into y. And what did I do really? I rotated it by some angle, and I stretched it, or I made it shorter. That's the underlying mechanism. Okay? All right, so good. So let's go to the next page. Yeah, so one way of thinking about it is that we rotated it, and we stretched it. So this is a key conclusion. So we rotated and stretched the vector, or the axes, or whatever it is. Okay? So here, we can write this out again. So we have the original vector x, and it becomes some other vector. We rotate it by an angle. Okay? And, if you think about it from here, it gets stretched by some factor that we're going to determine. Okay, so that's what matrices do essentially. So now you can see, going back to the computer graphics example of video games, if I had a mesh, now I can rotate that mesh, right? There is a matrix multiplication, there's a rotation matrix that I can apply to those points, and guess what? I can start flipping that first-person shooter or that car or whatever it is. I can also stretch it, so I can make it bigger, smaller. Do you see that? And so you can start playing with the dimensions of the mesh, or whatever it is in this case. In fact, there is a thing called a rotation matrix, just like there is a stretching matrix. So there's a rotation matrix and a stretching matrix. A rotation matrix. Okay. So there's a rotation matrix. And a rotation matrix allows you to rotate a vector by an angle theta. Okay, so it rotates by theta. And it has a specific form. So here we can use the classic example, A. And it's going to be cosine of theta, sine of theta, minus sine of theta, cosine of theta. So you guys probably remember this from some algebra class you took, the trigonometry. But essentially here, we just, what's great about this is you just figure out what the angle is. You want to rotate it by 90 degrees, for instance. Just plug in 90 degrees here, and then take this matrix and multiply times your point or your vector, and you're able to rotate that whole thing. Okay, so this rotates by that angle. There's also something called a stretching matrix. I'll write it here. There is a stretching matrix. And that, again, it's just the A, right? And that one looks like this. This is the value, and these are zeros. So where, you can say where this symbol is the stretching. And that's so that this happens, right? This is the stretching effect. So we just stretch that vector, such as taking that initial Rubik's Cube that we had and making it bigger or making it smaller. So we can do that. So here, let's actually corroborate this, right? So let's see if we can do this. So for instance, let's stretch by 2. So let's stretch a vector by 2. Stretch by 2. Okay, so I have my original 1, 3, the vector, right? And I'm saying that I can just use this matrix over here, right, as a stretching matrix, and I want it to be stretched by 2, so I plug in 2 here. All right, so let's do that. So this is going to be 2, 2 on the diagonal, and zeros over here, right? Do you agree? All right. So now I want to see what happens to x. I'm going to transform it into y, right? So how do we do this operation again? Remember, right? Okay. So that's going to be then 2, 0 times 1 plus 3. Do you see that? So we do 2, 0, 1, 3, right? 2, 0, 1, 3. So that's going to be 2. And let me erase this. That's going to be 2 here. And this is 0, correct? So this should be 2. Okay? Now the next one, right? So that's going to be, let's do that up here, 0, 2, 1, 3 plus. So that's going to be 0 here, and this is 6. So that's 2, 6. That's the vector that I got. So let's see if this is true. Let's, do the graph of this. Okay. Okay, so let's have like some values, 1, 2, 3. And then here we're going to have 1, 2, 3, 4, 5, 6, 7, let's say. Whoops. Okay, so let's draw the first one. The first one was 1, 3, the original one. So that's 1, 3, right? So then that's the original vector, roughly speaking, 1, 3. Now we've stretched the vector, okay, to 6. Do you guys see that? So if you notice, it just continues in the same direction, and we have stretched it out. Does this make sense? So we went from 1, 3, this was 1, 3, and stretched it out to be 2, 6. So by multiplying this vector times this matrix, we in fact do stretch it. So operations with matrices do rotations and stretching. Key concept. So now that we understand this, right, that's just the operation and the facts. We know that we can apply this to all the axes. Now we want to get more, closer into singular value decomposition, right? And the idea is going to be to look at several axes together that make up a basis for a vector space. So let's look at a simple example. And I'm going to keep this in 2 dimensions. But now I have a vector space of R2, right? R2. And it's going to be something like this. And notice it's a 2-dimensional space, roughly, that creates roughly a circle shape. Do you agree? It's just like, like a clock or something, right? So we have one axis, and we're going to call one axis V1, and we're going to call the other axis V2. Do you see that? So those are my 2 vectors that I have, okay? So what happens to this, and this call this a sphere because that's kind of the shape that is created. So what happens to this sphere or circle if we multiply it by a matrix A? Do you see that? So now you're going to apply a matrix A that you can apply here to each of the two axes, right? The basis of the vector space. And what do you do to them? You rotate them and you stretch them. Do you see that? And so effectively, you create a new vector space. So we then do a multiplication of these axes times A, which of course is a matrix. Now we know that, everything is set except the values inside the matrix. You know how I, in the previous example, said I wanted to stretch it by 2, therefore I created this one. But what if I wanted to stretch it by 4? Then this should have been 4, correct? If I wanted to stretch it by 17, then that would have been 17. Who decides what those values are? Well, in the context of machine learning, it is that machine learning, the AI decides, right? Because it has it has one thing. It has the input and the outputs, the training data. So it has a goal, which is to build a model that is really good maybe at predicting by having a high F measure. So it's just going to try, imagine multiple representations until that F measure does what? Goes up. You see that? So if I take my axes here, this one, and just start playing with A randomly, right? So let's say that I don't have a smart algorithm. I just randomly start plugging in values here. I change the shape of this sphere by rotating and stretching the axes, moving the points around, and every time I run my inputs, get my outputs, my predicted outputs compared to the real outputs, measure performance, right? We've done this, right? All semester so far. You guys have reported F1 measure scores. So if you have a bad model, what do you get? 0.10 F1 measure. You know that's bad. So then the algorithm says, okay, that's bad. I'm going to try another set of values in the matrix. And it keeps doing that, and eventually maybe it finds a combination that gets the F measure to 70. And it's like, okay, that's the best I can do. And that's the set of values that I use. So machine learning works that way. Usually it fills in the values. It fills in that 2 in the stretching matrix. It has to figure it out. Okay? But that's the idea. So we then take the space with the 2 axes here, multiply these axes by the matrix, and what happens? We stretch and rotate the vectors of the sphere, and the sphere becomes, in my example, this sphere is going to become an ellipse. Why? Just because I can show, yeah, exactly, right. So what am I doing for this to become an ellipse? I'm going to stretch some of them to be longer than other ones, right? Essentially. And I'm actually going to rotate it just for fun. So I'm going to do the following. So it's going to be more like this and like that. Do you see that? So if I draw this one now, and just so I can have a little bit of help, I'm going to make it a little bit more symmetrical. So then, right, you can see it's more, imagine this is round, should be a bit rounder. Right? But you guys agree then, right, that this was a circle, kind of like this. We rotated it almost by like, what is that, like 45 degrees, right? And also we stretched. So V1 became longer, V2 became shorter. Remember you asked this question before about the stretching. So here it becomes shorter, and this one becomes longer. And effectively, we're pulling the points away. Whatever the point, maybe the points here were like, maybe the points were like there, something like that. And now the points are, do you see? They have moved in the space, and that may help the machine learning algorithm to better understand the data and just be smarter. That's essentially the trick that it one of the mechanisms to understand and become smarter. All right? Does this make sense, guys? So that's essentially what is happening. You change the vector space where the points live so they can be better represented. This is called, we change our coordinate system, right? So Cartesian, right? Coordinate system. So we change it from a sphere like this to an ellipse like this one. So to an ellipse like this one, okay? Now I'm going to now put in a little bit of notation because this is really important, okay? So we have this notion of, I'm going to use blue here. We have this notion that we had these two vectors, v1 and v2, and then we did what? We rotated, right, v1 and v2. So in that case, they would be like the same vector, but just rotated. But because we rotated them, I'm going to change the name from v1 to u1. Do you see that? Just to indicate that this is now a rotated vector. And the other one, v2, is going to be u2. This is pretty important, okay? That accounts for the rotation. But also they were stretched by some factor. And so this one stretched it like that. So we're going to denote that part as O. So O1, right? So now it's O1 times U1 equal V1, essentially. Do you guys see that? To reflect the rotation and the stretching. And then for V2, it's going to be O2 V2 to reflect both the rotation and the stretching. This is pretty fundamental, okay? So the O2 is the length or the stretching, O2, O1 are the length or the stretching, and the other one is the rotation. So now, this is starting, we're going to formalize this a little bit more into an equation that's going to be really important here for our derivation of singular value decomposition. So I started with a vector space. So we started with a vector space made up of what? These axes, right? V1, V2, and we can generalize. If we had 4 dimensions, 5 dimensions, we can say V2. So we can generalize ... to Vn, right? However many, this applies if we have 1,000 dimensions. And we mapped, so we map by the matrix multiplication to a new space. And this is really important. Remember, in singular value decomposition, we've already done this. We had 7 sentences, 20 words, that represented that V1, and we mapped it into 7, 3, or 2, right? So we compressed it actually. But it's the same idea. Because actually, we can say, for instance, notice this is 2 dimensions and this is 2 dimensions. But as it turns out, imagine that this is even smaller, this axis here, like tinier, tinier, and tinier. So really, the points don't get much information from that axis, and essentially the other one is dominating, right? That's the one that's really stretched. So essentially, I can say for sure that it seems to me that U1 is more important than U2 for this type of problem, for instance, right? So that means I could drop even U2 and just end up with U1. That's the compression part. But so we started with a vector space V1, V2, Vn, and we mapped to a new space, all right? And the new space is made up of U1, U2, ... until UN. So the same, this is now the basis for the other space, which is no longer a sphere. It is now an ellipse, which is made up of these U's and these O's. So O1, O2, dot, 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 ON. Okay? Which are, remember, the stretching factors. So the U1s, and I'm going to use a different color here. These are called the principal axes. So these are the principal axes, okay, of this example that make up the vector space, essentially, the rotations. So it's a new coordinate system. And that's why the points are now, you can think of them as possibly being in a different location. And that's it. We do all this so that we can find other representations or organizations of the points and help out the data science. Okay? So now let's more formally put this more concretely. So there is, in fact, a relationship, as you can see, between V1 and its corresponding U1 times O1, right? That's obvious. Every axis is being mapped. So we can do that here. So more formally, we have now the matrix A, right? That was what? The rotating and stretching matrix. We do a matrix multiplication times V1, right? I'm just taking one vector. And what does that produce? O1, U1, right? O1, U1. So I'm saying I take V1 times A equal U1 times O1. Then I can take V2 times A, and that produces U2, O2. Do you see that? And this is how I can create new vector spaces. One of the key concepts in machine learning. So I can do same A, matrix multiplication, but rotation and stretching matrix, A. And now it's going to be V2, so that is then O2, U2, like that. There you are. So that is your equation. Okay, questions? So then we can now represent this as a little bit more in detail. We're going to say this is matrix A times all the vectors that make up that axis. So that's going to be V1, V2, I'm going to generalize dot, 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 Vn. Right? So you multiply times all of them, and that produces then, for the U, U1, U2, dot, 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 Un. But these have to be multiplied by the what? These things are called the singular values, the stretching factors. And interestingly, because of the way that this works, we only have one O, O1 only applies to U1, right? You saw that. And then U2 has O2, U3 has. So a way to write this is something that you had seen before in the I matrix that you saw at the very beginning of the semester. We put the O's in a matrix on the diagonal only. Dot, 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 O-N. And the rest of the values are going to be 0 when they're off diagonal. Why does this work? Let's do this, right? Let's do that same operation. So I take the vector times the column, right? They have to match in dimension. So remember, all of these are 0, right? All of those are 0. Only this is a value. So if I do this, I'm going to have what? Oops, let me use that. Okay, I'll change the blue. So I'm going to have U1 times O1. Yeah, right? Times O1. Okay. Plus U2 times what? 0. Very good. Perfect. Exactly right. 0. And it's actually zeros for all the other ones. So guess what? We get the right thing, O1, U1, and the rest are zeros. So we get, in fact, the vector that we want. Then we do this again. Let's say I do this times this, right? So now I take, let's do it up here, U1 times what? What is this value? 0, because all the values off diagonal are 0. So U1 times 0 plus U2 times O2, the corresponding value. Do you see that? And then we do U3, let's say, times what? 0. So you can see that only this one stays and the other ones become 0. So this is perfectly correct. But this is important, actually, the way that I'm formulating this, because from now on, the singular value decomposition will always give us one matrix of the 3 that it gives us that is going to be like this, which we can call the diagonal. Okay? Do you guys see that? It just does that, right? So it's guaranteed to give you one of the matrices where all the values are off diagonal are 0, and only the values on the diagonal are going to be values. But it's the same operation as before. A, the matrix, rotation and stretching matrix, times the basis vectors of V becomes vectors U times its corresponding O's. So the rotation and the stretching. Okay? And that's the same formulation here, right? So V1 becomes O1U1, V2 becomes O2U2. This is extremely important to understand because it's all about the points moving into another space, right? Or in that idea. Okay? But I'm putting it now as a formula because singular value decomposition is a formula, but a formula of vector spaces. In fact, another way of saying it is I have this vector space, right? I have this vector space, and with SVD, I create, you could say, at least 2 more vector spaces and this diagonal. So I create, but let's just generalize. Let's just say from this vector space, I create 3 new vector spaces. And that is the key idea, okay? That is the key idea. So we'll see that. So now I have A times V equal U times O, okay? So we have that formulation. Oh, actually, and let me give it letters now. So then we can call this, I'm going to change the color here to green. All right, so this one we had labeled already. It's A, the stretching and rotating matrix. And now we can say that it is M by N, which is really great, actually. This matrix is M by N. What is M by N usually? Our data. Our data iris, M, 150, N is 4. So it's, our data fits nicely here into that A. Okay, this one we can call V, like that, and I'm going to use like V hat to indicate that it is the symbol that represents it. This is an equal, of course. This one over here, I'm going to say it is U hat, just to indicate it's these vectors, right? So we had 10, n vectors here, let's say 10, we have 10 vectors here. We always can get the same number of vectors, but there's going to be a nice trick that we're going to see in a second. But just keep in mind right now, like in our previous example, we were going from R2 to R2. Oh, and I wrote, that should have been like that. You see that? So we're going from R2 to R2. This is really important. What does that mean? It means that we go from V1 all the way to Vn, let's say V20, to U1 all the way to U20, right? So Un. so that you can have the same number of vectors just stretched and rotated. And every U corresponds to an O, but we conveniently write the O's this way. And I've proven already to you guys that O1 will correspond to only U1, right? Because of the matrix, the properties of the matrix multiplication, as long as all the values here off diagonal are 0. All right? So this is important. So now we're almost done, by the way. So this is the derivation of the singular value decomposition. So we label this as A times V. Remember, this is now represents all these vectors equal U. And this last one, we can use the letter, this symbol here, to indicate that this, you can use hat, doesn't matter. I usually just call it the diagonal, so I remember, okay, the diagonal is where all the values, are on the diagonal, the O's, etc. So now that I know this, I can actually, instead of always writing out this, I can just write a shorter equation, right? And I'm going to write it up here so that you guys can see it, probably in orange maybe. All right, so the formula now would become A times V equals, and V hat, U hat times the diagonal. Do you guys see that? There you are. So that's essentially now all this logic, just so that we could arrive at this, right? Which represents that this is the basis of one vector space, this one, right, the 3 axes, times some matrix for rotation and stretching, and guess what it produced? Another set of axes, right, another vector space, but we break it up into rotation and stretching, the O's and the U's, essentially. That's it. All right, so that's the intuition, or the shorthand, if you will, of how, or what you can call this. Okay, so then let's move to the next page, because that one's getting pretty busy. Okay, so we have, so we've started with A, V1 producing O1, U1, right? A, V2 producing O2, U2, A, V3 producing O3, U3, right? Dot, 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 right? So, this just depends on the size of my vector space. So we convert one set of orthogonal coordinates, remember orthogonal just means 90 degrees, to another set of orthogonal coordinates. That's it. All right? So that's, and I've talked about that. And again, this is called an orthogonal basis or orthonormal basis. But, all right, so here comes the last part of this that now gives us our singular value decomposition. So if you remember, in the code that we did, when we looked at the k-means example, you can refer back to the k-means, guys over there in the back. So if you remember the k-means algorithm, we had, Python, right? So a function like np dot, what is it? I wrote it down here. Linear algebra dot svd of x, right? And that would return 3 matrices which are U, S, and V, any letter that you want. But this is key. Singular value decomposition takes some matrix X and breaks it up into 3 matrices. And we'll see this in the next lecture. We'll do an example of this. And this is great. Now it's like you can break it into different parts and analyze it, right? And from there you can do things like compression and many other things. This is a very important procedure. But this is the key. So if you look, right? So I have an X, I have a US and an SV. That's what the function was doing. in code. But if you look, that looks a little bit like this, don't you think? I have 4 matrices here, right? So maybe what I need to do is move one of these matrices to the other side, and then I will have 3 matrices on one side and just 1 matrix on the other side, which is similar to this. 1 matrix on one side, 3 matrices on the other side. Do you guys see that? That's the insight, right? So that's what we're going to do now. So we are going to start with, and I'm going to move to a new page for this. We are going to start with A, V equal, and V hat, to be consistent, equal U hat, and this diagonal. So remember, the O's, the U's, the V's, and the X matrix. Now, what can I do? What I can do is, I can always multiply. Like if I do this, then obviously I can do this, right? We know this. If I do 4 over here, then I just do 4. It's kind of the same thing. So I'm going to then do an operation, but with matrices. I'm going to say, and I'm going to select a specific matrix. I'm going to take V, and I'm going to say I want that V, but something called the inverse of V, which is equivalent to saying I want 2, and I want 1 over 2. Do you guys see this? And this is something that you did a lot when you were in high school to cancel out something. It's a very common trick, and it applies just the same in linear algebra. And so we do that. But the trick is that I want to move the V to the other side. So I'm going to do A, V hat, and now I'm going to multiply this one times V minus 1, the inverse of it, equivalent to this idea, equal to U hat, and then V minus 1. Do you see that? So by having this, there's a rule that will say that V and V inverse of itself is 1. So then this becomes 1 over here, and now I just have A equal U V minus 1. Do you guys see that? So I was able to get the U, the diagonal, and the V on the other side, and now I just have A. This is a guaranteed property that any A that is m by n can produce these 3 matrices. That there will be a solution to that problem. And that's the key. So now that I've done that, we do another trick, which is to say that the V inverse is equal to something called the transpose, which you guys already did this in the tensor operations, right? We moved the matrix. We did that example. So we just rewrite this for convenience to say U V. Do you guys see that? This is the reduced singular value decomposition. You can see that it all ties still to this idea. So essentially, we are in fact going from one space to another space, right? And that's essentially it. So now, here, right? So we just did this. So we can say this is called, this representation, this is called the reduced singular SVD, let's just say SVD, singular value decomposition. And I can't stress this enough, right? So we did all of that, tied it to the vector. It's tied to the vector spaces, but there's a theorem that says that any A that is m by n can absolutely always find 3 matrices, U, diagonal, and V, that that are equal to A, essentially. So A can be broken up into 3 matrices. And why that's important? It's important because then now you can look at these 3 instead of just looking at A. It's like you remove noise, you You see details that you weren't able to see before. And I'll do a second example on Tuesday for you guys of the Netflix example, right? So we'll look at specifically movies and users, and from there we'll figure out categories like sci-fi, romance, and I'll give you a hint in a second. But let me just finish up this, okay? So what have we done? So we just did a little bit of math, right? Algebra, rearranged the terms essentially in terms of our U, our V, and our diagonal and our A. And we arrived at this representation, which is called the reduced SVD. Let's say you wanted to interpret this in the terms that we've been discussing it so far, right? So what did we say initially? What does a matrix do to a vector? Yep, exactly. It rotates and stretches that vector, right? So then, okay, well, what can I say then about A in this context? Let's write it down. So, A, right, this matrix A over here, can be decomposed. So A can be decomposed into three matrices where, so in the three matrices, so VT, right? So, or, oh yeah, so here this should be VT, sorry. So because the -1 here, did I write that part down? Yeah, I wrote it here. So V -1 is equal to V transpose, so I just changed the term, okay? So VT, so we can say A can be decomposed into three matrices, and let's say, and VT is a rotation. U hat is a rotation. You agree, right? They're rotations. And what is the diagonal? You know this. What was the diagonal? The O's, right? What were the O's? They were stretching. Remember? So we were stretched. So remember we said, you know, the U means we rotate and the O means we stretch, right? So that was the intuition. So then we are saying here, and the diagonal is a stretching. And that's it. We take our space and we just like rotate it, pull it, and so on. So another way that we can say this potentially is, so A is a rotation VT times a stretching diagonal times a rotation U. That's it. That's like the magic of it. So finally, we will conclude, and I've already concluded this, but it's just right here. There is in fact a theorem. So finally, there is a theorem, like a proven thing. This is proven theorem that, and this is important and key. Every matrix, not, remember, A was initially a matrix with values for the purpose of rotating and stretching, right? That's what A was. But now we can change A to be something else, right? It's just a matrix. So here, every matrix A that is M by N has a singular value decomposition decomposition like the one such as A equal U hat, the diagonal, and VT hat. Okay, we've said this already, but the key insight here is any matrix, it just says any matrix M by N. What about iris? Iris was not a rotation and stretching matrix, right? What was iris actually? Our data. But it's still a matrix, correct? And it's still M by N. I've been saying this for a while. Iris is M by N. So iris is 150 by 4. So essentially, instead of A, we can replace this with X. Do you see that? And now our data can be broken up into, if we want that. It's guaranteed. And then when we look at this, it gives us all kinds of information. Okay? So all this is doing is creating a relationship between the vector spaces, old vector spaces and new vector spaces. That's essentially what it is. You all agree that iris is a vector space, correct? R4. So great. So we can now represent it as another space with dimensions up to 4. But from there, we can do other things with that information. Okay? So that's the key thing. And we will see that in the next lecture. Today, my point was just really to get to here and to show you this relationship, right? So that because X is M by N, and the theorem says that every matrix M by N has a singular value decomposition, therefore, we can, in fact, decompose X into these three. And the meaning, the underlying meaning is, this was a vector space, so this is another vector space, much like we had the sphere become the ellipse. Very good. You got it? All right, so that's very good. In the next class, I will give you a more concrete example. And just to kind of give you a hint now, it'll be like movie reviews. So my data is going to be something like this. It's going to be, I can't remember, I think users are the rows and movies are the columns. So this would be what? The Matrix, Star Wars, but also Casablanca, You've Got Mail. Do you see that? And here I have users, Johnny 1, Mary 3, and so on. But this is X. You agree that it's M by N, probably 100,000 users. I don't know how many movies there are. Let's say 1 million, right? So, right, a lot. Netflix probably has has a lot, right? And what does SVD say? I'm able to decompose this into 3 matrices. M, right? The diagonal, and another matrix over here. So the U's, let's say U, V, and the diagonal. Do you see that, guys? But here's the thing. Here's where this pays off. All I knew was about, here is like the matrix. And this is Casablanca. What is Casablanca? Like an old romantic movie, I think, right? Let's say it is. You've Got Mail, also either a comedy or a romance. But the Matrix is like sci-fi, right? Star Wars is sci-fi. So here on this end, you still have users, but now these columns are no longer the movies. They are a new basis that you just created. So the V's, it's like the V's were the movies, and now you have the U's, which are something completely different. Do you guys see that? So that's the intuition here. And so we break this up, and now this will become we're just going to call it, let's say, singular value 1, singular value 2, singular value 3. But when we look at this example and we look at the data, guess what this becomes? And what does this one become? Do you guys see how valuable that is? So essentially, the algorithm figures out categories such as movies related or users that like sci-fi, users that like comedy, and so on. And what happens on this other side? This other side has The Matrix, Casablanca, You Got Mail. What do you have here in the rows? It is no longer the users. It is S1, S2, S3. And as it turns out, then, the movies that are these two movies are romance, right? So let's say that S2 becomes the romance category, then that's going to be 20, 30, and this is 1. Do you see there's a difference there in the values? And let's say that I have here The Matrix and Star Wars, right? Star Wars. So, oh, there's 3 movies here. No, I just added. So this one also has 1. Do you see there's a difference? So now for this category, S1, let's say this is going to be sci-fi. So guess what? For The Matrix, this is going to be 70. For Casablanca, this is going to be what? Who can tell me? A different number, so possibly 2. What about Star Wars? Closer to 2 or closer to 70? Yeah. So it would be 65. What about You Got Mail? Closer to 70 or closer to 2? 2. So let's say 3. Do you see that? Do you see that this is useful now? It never says, oh, S2 is sci-fi, S1 is comedy. It's not going to tell you that. But if you start to analyze it, you will see that similar movies are going into similar categories, like I just did. And that's the power of something like this. Make sense? All right, so, and that's why this is important, because you end up with these categories. You have 1,000,000 movies, but really you just need 30 categories, and that might be enough. So your space gets reduced from movies to genre, right? That's what that's called, genre of movie. All right, guys, so don't worry about this example. This is the example we will start with next week. All right, we'll do a whole example by hand, but you can see now I brought together everything, and we tied how we have these vector spaces. We have this matrix multiplication that is critical for stretching and rotation, and we can essentially then decompose one matrix into 3 matrices and essentially find our data in different vector spaces. Okay? All right, guys, so let's stop here for today. No homework this week.